Welcome to Lecture 1 of the Algorithms class. So today I'd like to start by talking about some overarching goals that we're going to have in this course. So in some sense, the big goal of this course is to answer the following question. How fast is an algorithm? And I'll almost always abbreviate the word algorithm just with algo, just to keep things quick. And so in some sense, we want to understand if I have an algorithm that's designed for doing a particular task, how long does this thing take to run? And so we've talked very briefly in some of the synchronous sessions about what this might look like, but let's start to get a little bit more precise. So let's ask this question with a little bit more in a more targeted way. And so instead of just saying how fast is an algorithm, let me ask, how fast is an algorithm as a function of the size of its input? And I'll abbreviate function with FCN frequently here. And this is really the big question, the core question that we're going to be chasing down throughout the course of the semester. Is how does the input size for an algorithm kind of relate to the runtime of the algorithm? And so to be able to answer this question in a precise way, we need to be able to identify what we mean by input size. Right? We're trying to literally define a function, as in we're trying to define something that looks like t of n, where n is this input size. And to be able to make this function well defined, we need to be able to be precise about what we mean by this concept of input size. Okay, so in some cases, the input size is very obvious. Okay, so what might an obvious input size be? Well, if we are looking at something simple like an array, so an algorithm where the input is an array of numbers, then the input size is almost always going to be the length of the array. So if it's an array algorithm, length is what we care about. Sometimes it's a little bit less obvious. So if we are dealing with an algorithm that operates on a matrix, then the input size might not just be a dimension of the matrix, but it might be the total number of entries in the matrix. So suppose we have a matrix that is of size m by n, so it has m rows and n columns. I'll say m by n. Then what's the input size? Well, to be strict, we want to describe the input size as the number of entries in the matrix. So how many entries are there in an m by n matrix? Well, there's literally m times n entries, right? Because we're talking about the size of a rectangular grid. So mn would be a valid input size. Okay, but occasionally we'll want to express, for a square matrix, for example, that's n by n, we'll want to express the runtime of an algorithm in terms of n, just because it's a simple parameter that ends up repeating itself again and again. In some cases, if we're dealing with a numerical algorithm, we might end up with something slightly unintuitive. So let me explain what I mean. So for example, what if I asked you to write an algorithm that determined whether a given number is a prime number, right? So for example, we could call this the Primality Test. So in primality testing, we get an integer, and the question is this integer prime or not? And it feels like if the integer is, say, capital N, so input is n, then we would be tempted to say that n is the size of the input, but that wouldn't quite be correct. because what we usually care about in algorithms isn't the value of the input, but it's the number of bits that it requires to represent the input. So if the input is literally a number n, then the input size is the number of bits. Right? So how many bits are there to represent an input that has a value of n, right? A number that has a value of n. How many bits does that take? Well, roughly log 2 of the number of bits. And the exact number is the floor of log 2, log base 2 of n, plus 1. Okay? And then another class of problems we'll be thinking about is graph problems. So if we're dealing with a graph problem, so in this case, and we'll look at a lot of these later on in the course, so things like flow problems on graphs, where we want to understand how much of a stuff can we force through a graph, or routing problems on graphs, where we want to understand what's the fastest way of getting from point A to point B on a graph. In a graph problem, what's the input size? Well, here it depends on how we've written the graph down. So here it depends on, and we call this the representation of the graph. Right, so if we've represented the graph as a list of all of the links in the graph, that representation is going to take up a different amount of space than if we've represented the graph as a grid of all the different nodes in the graph with corresponding edges listed in a matrix. And we'll get to all of these concepts as we get to them, but the key thing is the size of the input, the exact numerical value of the size of the input, depends a lot on what kind of a problem we're actually looking at. It depends a lot on what the input is actually shaped like.